Most people believe the plants we grow today replaced older crops because they were better, higher yields, more efficient, more advanced. That story sounds logical, comfortable even, but it leaves out something important. Plants were not only selected for how well they fed people, they were selected for how well they fit a system that values uniformity, predictability, control. Crops that mature at the same time, crops that ship well, crops that require yearly inputs, crops that keep farmers dependent on seed suppliers, fertilizers, and chemicals. Plants that didn't fit that system weren't banned, they weren't outlawed, they were simply studied, documented, and then slowly removed from focus. Today we're going to look at 5 of those plants. Not myths, not legends, real plants, grown for centuries, proven in research, replaced not because they failed, but because they worked too independently. At number 1 came the winged bean. Its scientific name is Phosocarpus tetragonalobus. People originally planted the winged bean because it solved several problems at once: protein, soil fertility, space, nutrition. Nearly every part of the plant could be eaten: leaves, flowers, pods, seeds, even underground tubers. For small farmers in tropical regions, that mattered. Historically, the winged bean was cultivated across Southeast Asia and parts of the Pacific. It wasn't a novelty crop, it was a reliable one. Families saved seed, communities passed down growing knowledge. The plant fixed its own nitrogen, meaning it improved soil instead of exhausting it. In the 1970s, scientists took a closer look. Formal studies confirmed what growers already knew. The seeds contained protein levels comparable to soy, in some cases higher. The plant required little fertilizer. It performed well in poor soils. On paper, it should have become a global staple. But here's the problem. The winged bean did not create dependency. Farmers could save seed. Fertilizer use dropped. Crop rotation improved soil naturally. There was no strong incentive to replace it with a patented, input-heavy system. Soy filled that role instead. Soy could be scaled, patented, and tightly integrated into chemical agriculture. The winged bean wasn't erased, it was simply left behind. At number 2 came perennial relatives of wheat. Not the modern wheat you see today, but older perennial grain species and breeding lines that didn't need to be replanted every year. People planted these grains because they stayed in the ground. Their deep roots reduced erosion. They accessed water annual crops couldn't. They stabilized soil and survived droughts better than shallow-rooted wheat. Historically, early agriculture relied on mixed systems, annuals and perennials grown together. Perennial grains didn't produce identical harvests year after year, but they produced resilience. The disadvantage from an industrial perspective was consistency. Perennial grains didn't mature uniformly, they didn't fit mechanized harvesting schedules, and they reduced the need for yearly seed sales. Annual wheat replaced them because it worked better for machines, contracts, and global shipping, not because it was better for soil. The shift wasn't sudden, it was gradual. Research funding followed crops that fit the system. Extension programs promoted what could be standardized. Over time, farmers adapted, not always because it was best, but because it was supported. This pattern repeats. Plants that regenerated themselves, plants that improved soil, plants that reduced inputs. They weren't dramatic failures, they were quiet mismatches. And that brings us to the next plant, which didn't just grow food reliably, but refused to stay gone once planted. The third plant on this list didn't disappear because it was weak or unreliable. It disappeared because once you planted it, it refused to leave. At number 3 came the Jerusalem artichoke. Its scientific name is Helianthus tuberosus. People planted Jerusalem artichoke because it was dependable. It didn't care much about soil quality. It tolerated cold, drought, and neglect, and most importantly, it produced food underground, calories you could count on even when above-ground crops failed. Historically, this plant was cultivated by indigenous communities across North America long before modern agriculture arrived. It was a winter food, a famine food, a plant you could return to year after year without replanting. The tubers stored well in the ground. You harvested what you needed and left the rest. No storage buildings, no refrigeration, no annual seed buying. That was the advantage. It was also the problem. From a modern agricultural perspective, Jerusalem artichoke is difficult to control. It spreads easily. It doesn't fit clean rows. It doesn't disappear when the season ends. Once established, it becomes a long-term presence. Industrial farming prefers crops that start and stop on command, crops that clear the field completely, crops that allow the land to be reset each year with machinery and chemicals. Potatoes replaced Jerusalem artichoke not because they were nutritionally superior, but because they were easier to manage within an annual system. They could be planted, harvested, and erased on schedule. Jerusalem artichoke didn't cooperate with that rhythm. At number 4 came one of the most extreme examples of replacement: duckweed. Often grouped under Lemna and Wolffia species. People historically didn't think of duckweed as a crop in the modern sense. They thought of it as a food source that simply appeared. It grew on water. It multiplied rapidly. In some cultures, it was harvested for animal feed. In others, for human consumption. What made duckweed remarkable was speed. It is one of the fastest-growing plants on Earth. Under the right conditions, it can double its biomass in a matter of days. Some species contain protein levels comparable to soy, without soil, without fertilizer, without large land requirements. In controlled studies, scientists noted its efficiency, how little input it required, how much output it produced. That efficiency was exactly why it didn't fit. Duckweed doesn't require fields, it doesn't require tractors, it doesn't require seed companies in the traditional sense. It grows in ponds, tanks, and slow-moving water. The modern food system is built around land ownership, large equipment, and centralized processing. A protein source that grows on water and regenerates continuously doesn't slot easily into that framework. Soy became the dominant plant protein instead, not because it grew faster, not because it required fewer resources, but because it integrated cleanly into existing infrastructure. Duckweed wasn't pushed out aggressively, it simply wasn't scaled, marketed, or prioritized. Notice the pattern forming. The plants on this list weren't replaced because they were inferior, they were replaced because they disrupted predictability. They complicated logistics, they reduced dependency, they didn't align with centralized control. Once agriculture shifted toward uniform harvests and global supply chains, plants that worked locally, regeneratively, and independently became inconvenient. Which brings us to the final plant on this list, one that didn't just feed people, but challenged the idea that grain had to be fragile. The 5th plant on this list wasn't fragile, it wasn't small, and it wasn't obscure. It was powerful. At number 5 came amaranth. Its scientific name is Amaranthus species. People planted amaranth because it fed them reliably in places where other grains struggled. It tolerated heat. It tolerated drought. It produced seeds rich in protein and minerals. And unlike many grains, amaranth didn't strip the soil as aggressively. Historically, amaranth was a cornerstone crop in parts of Central and South America. Entire civilizations depended on it. The seeds were stored, cooked, ground into flour, and used in ceremonial foods. It wasn't a backup crop, it was a primary one. From a nutritional perspective, amaranth didn't behave like a typical grain. It contained a more complete amino acid profile than wheat or corn. From a growing perspective, it didn't demand perfect conditions. And from a systems perspective, that created a problem. Amaranth did not respond well to monoculture farming at massive scale. It didn't mature uniformly enough for industrial harvesting. It didn't fit the same milling infrastructure as wheat, and most importantly, it was easy to save seed from. Corn and wheat replaced it because they aligned better with centralized processing, storage, and trade. Not because they were better for people, but because they were easier to control. Now step back and look at all 5 plants together. Winged bean fixed its own nitrogen and reduced fertilizer dependency. Perennial grains stayed in the soil and didn't require yearly replanting. Jerusalem artichoke returned year after year without permission. Duckweed produced protein without land. Amaranth fed people without exhausting the ground. These plants had something in common. They reduced inputs. They worked locally. They resisted standardization. The modern food system didn't remove them out of malice. It simply stopped supporting them. The modern food system didn't remove them out of malice. It simply stopped supporting them. Research funding followed different crops. Education followed different priorities. Farmers adapted to what was subsidized, mechanized, and scalable. Over time, knowledge narrowed. Not because the old plants failed, but because the system changed. And here's the part that matters now. None of these plants disappeared. Their seeds still exist. Their genetics still exist. Their benefits still exist. What disappeared was attention. Today, people are rediscovering these plants not because they are trendy, but because the problems they solve never went away. Soil degradation, input costs, climate stress, food insecurity. These plants were never meant to replace everything. They were meant to balance systems. The mistake wasn't abandoning them entirely. The mistake was forgetting why they worked. If you understand plants, you start to understand agriculture. If you understand agriculture, you start to understand incentives. And once you understand incentives, a lot of history suddenly makes sense. This wasn't a story about 5 forgotten plants. It was a story about what we chose to prioritize and what we quietly left behind. If this helped you see food differently, soil differently, or systems differently, you already understand why this channel exists. Strong plants didn't disappear. They were simply replaced. And now, they're being noticed again.